time-dependent setting, in particular how Floquet's theorem leads to some interesting physics in the system. And I've left this space here a little bit blank for a reason, which I'll come to in a moment. But first, let me, just before I don't want to forget, so let me make sure to thank my collaborators, R.G. Kundu, who was a postdoc with us in Indiana, and he's here now at Technion, my former student, Sean Wu, my more senior collaborator, and Rovis.
Doesn't look like it.
And Babak Saraja, and our guest of honor as well. And of course, can't forget funding. So I left that little space there because I have a subtitle here, How ASA Got Me Started on Something Interesting Again. So I thought just very quickly for the first couple of slides, I would say a little something about how I first got to know ASA. And this was in the context of a problem that I was working when I was a postdoc. It was a topic that Marcus Büdeker introduced to me, and this was the question of tunneling times. And basically the question is, when a particle is tunneling, going through quantum tunneling, how much time does it spend in the classically forbidden region? And there's a small but very active community of people who work on this problem and have done so for a long time. There's a number of answers to the question. And some of them give you a strange result in the case of a very opaque barrier that you find the tunneling time vanishes. And so there have been people who argued about whether this means that there's some kind of faster than the speed of light motion going on in the tunneling process. So Marcus actually told me about this. So I started to think about it. One idea I had was, well, maybe we can understand what's going on if we could really look at not just sort of an average tunneling time, but really figure out what the distribution of tunneling times is, and if we could figure out what one really means by that. And so I was sort of puzzling over how to do this when I came across a paper by Asa and Steve Kittleson, which I think was part of Asa's thesis, right? And basically this paper develops a method by which you can break up a path integral into pieces that are in well-defined regions of space and kind of knit the whole thing together so that you can get the path integral for a bigger system. And you can use different approximation schemes in the different regions as is appropriate. When I saw this paper, I got very excited because I realized you could modify it to, I don't want to go into the details, but to answer the question that I was trying to get at. I was able to use what he did there for my own purposes, eventually got my own paper out of this. And so I sent that paper to Asa, and that's the first time he heard about me. He sent me back a very polite note afterwards, and we've been talking ever since. So I'm very grateful for that. So fast forward to summer of 2010. I went to Aspen, and Dan and Asa were talking about this paper over here, which turns out to have a lot of interesting things in it. Photovoltaic Hall effect and graphene. And this is about what happens basically when you shine light on graphene and how this modifies the electronic spectrum and what are the interesting properties that come from that. So this paper, I think, has actually inspired a number of people in the audience, and a lot of people have been sort of following up on some of the ideas that come from this. So to introduce the topic, actually what I thought I'd do, this is a picture from the paper, and I thought we'd just go through the panels one by one to really understand what we're talking about. So in this first panel over here, they're just showing us the Dirac cone, or one of the Dirac cones in graphene, and this black circle here is supposed to indicate, let's say, an electric field in the plane that's rotating around at some frequency. And very importantly, we're going to imagine that the light is shining on your sample normally, so that electric field is uniform across the plane. And because it's uniform across the plane, there's going to be some electronic structure that's got a well-defined momentum, crystal momentum, associated with this. Now, this is a time-dependent problem. One has to solve time-dependent Schrodinger equations to look at the electronic states. And this is an example of a problem that's governed by Floquet's theorem, which is actually really the more general statement of what we often call Bloch's theorem in solid-state physics. And basically, we're looking at a problem where you have an operator, the Hamiltonian in this case, that you'd like to, in this case, you'd like to, well, basically you want to find some kind of eigenvalues of this operator. And when you've got this symmetry, this translational symmetry, discrete translational symmetry in time, you can show that the solutions are going to have a form, the time-dependent Schrödinger equation, that are a piece that's periodic in time times a phase factor. And you can see that the way this phase factor works, there's a coefficient over here that looks very much like an energy, but it's not exactly the same thing as an energy. It's called a quasi-energy. And just as in Bloch's theorem, the piece that's in this coefficient here comes inside some kind of limited interval, where you can always put it inside a limited interval. So you can call this a Floquet zone in analogy with a Brillouin zone. Okay, so we've got this electric field that's circulating in the plane. So we can implement that just by putting in a vector potential that also circulates in the plane. And this can just be done by minimal coupling to momentum. And so if you plug this into the time-dependent Schrödinger equation, the kind of eigenvalue problem we've got to solve looks like this. So we get a bunch of solutions. You get a bunch of eigenvalues, which are these quasi-energies. And just as in solid-state physics in momentum space, you can basically represent things in different ways. In particular, you can have a repeated zone scheme, and that's what's being shown over here. So we can kind of understand this as the Dirac cone being repeated up and down by basically being shifted by the frequency omega and making many copies. And then when we get these different copies of the Dirac cone kind of meeting up, kind of coming near each other, the potential here, the vector potential, actually admixes things and causes a level repulsion. And so you get gaps opening up. So the whole thing breaks up into what looks like electric bands. This is another picture showing us these gaps that open up and basically get larger and larger as you make the light basically a little more intense. So this is actually something that has actually been observed experimentally, not in graphene, but in another Dirac system. This was basically on the surface of a topological insulator. Nugetic has done some ARPIS experiments, and it's a little hard to see when you first look at it, but they show some data and do some careful fitting and show that indeed you can get gaps opening up in the Dirac cones on the surface when you shine intense light on the system. And in fact, if you compare to the gaps that you get from the Aoki theory, the match is extremely good. They actually predict quite well what those gaps should be. Okay. The last panel here is showing their computation of Barry's curvature inside the band. If you integrate this up, you discover that the band now has, the Floquet band, will now actually have a Chern number which generically is non-trivial. Rarely is ever zero, which is non-zero integer. And there's different ways of looking at this. One is to think in terms of the isospin, because since we're talking about graphene, our wave functions are two-component spinners, with the entries being the amplitudes on the two sublattices. So we can turn those spinners into three-dimensional vectors if we like, and use those vectors to use the Chern number for the band. And the interesting thing is that even though these vectors are moving around as a function of time, if you just take a snapshot, you can compute the Chern number, and that will not be able to change as time goes on, because this is something quantized. It's not something that can vary continuously. So this is something that Dan was very interested in his usual way. He was able to write a program in about 15 minutes and basically compute the band structure and also compute the Chern number for the system. So I don't know if you remember, Dan, you actually produced these pictures. So, and let's pay attention to the blue pictures here, because this is the actual quasi-energy structure. This is at a relatively high frequency, basically showing more or less almost the same band structures you get with graphene, except, as I said, you see somewhere between these two frequencies a gap closing, so the bands can actually exchange churn numbers. And I'm going to want to talk about how that actually happens a little bit below. So one of the things Aoki and Oka pointed out was that you can get a Hall conductivity out of this. It doesn't have time reversal symmetry. The circulating electric field breaks that. And if you just look at Berry's curvature in the band, you can basically, in the usual way, write down the Hall conductivity for a closed system. But there is this issue of how do you occupy the bands. This is one of the topics that we talked about that summer a lot. Is this quantized? Well, if this has the usual form of occupy one band and completely not occupy another, you'd expect it to be quantized. One way to look at a hint of whether you can have some kind of quantization like this is to search for edge states in a finite size system. So this is a calculation of a ribbon with zigzag edges, and you just force diagonalize the Floquet Hamiltonian, this object over here. And indeed you find that if I had closed the system into a nanotube, given a periodic boundary conditions, there would be a gap in the spectrum, but when I have the open edges, you can get edge states. The wave functions, and you can convince yourself they are indeed localized at the edges. So a lot of people have looked at these sort of edge state structures, and there's actually a number of things to say about them in this Floquet setting. I'll just point out a few papers out about this. So it's a big question if you want to do a system that doesn't actually have a boundary, and you don't want to do this directly by looking at a system with leads, what determines these occupations? And the reason, one way to see that this is not a simple question, for example, some people in the literature have actually simply used the Fermi function over here with the quasi-energy as the energy at the end. And you can see that that is not necessarily sensible by comparing, for example, the quasi-energy to the average energy of a given state, time average energy of a given state. And so in places, particularly where you have these near crossings or these avoided crossings, that average energy can be very different than the quasi-energy, right? If I look at the state over here, the average energy is way up here. So why would I be using the quasi-energy down here to characterize whether or not the system is that state is occupied? This is a pretty hard question. Again, a number of people have been working on this in this context. Again, I'm just going to show a couple of references, but it's far from an exhaustive list. Okay, so we wanted to do something simpler to try to address this, and so we had the idea of looking at this as a scattering problem. So here we took actually basically on the computer in some sense a piece of graphene, and very importantly, when we did this, we treated this in the continuum, and we put this basically contacted by explicit leads. And the idea is the light is shining in here, and we're going to have all the dynamics of the electrons be quantum coherent with no dissipation of any sort, whereas we'll have dissipation in the leads. And we can imagine, for example, that these are very highly doped regions that could, let's say, screen out the light, and so we could maybe sensibly talk about chemical potentials for our two leads, and just have any dissipation that's actually going on go on with the leads, but we won't deal with it explicitly. So you can treat this as a scattering problem. There was a paper for the static version of this that attracted a lot of attention in the graphene community that Carl Bainacher and his co-workers worked through. And he did a very pretty result, and I'll show it in a moment. And that kind of inspired us to look at this beyond. So here's the result that we got from these calculations. First, the red crosses are the case where there's no light shining on the sample. So this is reproducing the Carl Bainacher result. The interesting thing that you find here is that for small lengths of your sample, small distances between the leads, this is a log-log plot, so you're getting a power law. The power law here is just showing up that conductance falls off as 1 over L. So the system actually has a conductivity in this situation. And that's interesting because there's no impurities or anything. The conductivity is really just coming from the semi-metal nature of the graphene itself. But if we make the system long enough, eventually you're going to notice the finite width of the sample. There's a transverse gap from that finite width, and then the conductance will fall off exponentially because you get basically long width. So now we can contrast that with what happens when we shine the light on the sample. You see again, roughly, it's not exact, but roughly, we get a straight straight line in this log-log plot, but it doesn't have the same power law as the 1 over L. It's actually got a smaller power law. And then moreover, when you go to larger systems, rather than getting a decrease in the conductance, you actually get it leveling off. And that's just the signal that the system has edge states. No matter how long I make the sample, I'm able to conduct electricity from one mean to the other. Now, this behavior here was very puzzling and sort of kept us from finishing this up for a long time. But eventually we understood what was going on, had to do with the zone-folding phenomenon. I mentioned on the last slide that we were actually doing this in the continuum, which means that effectively the bandwidth was being taken as very large compared to the frequency. If that's the case, we get a lot of folding, a lot of pieces of the energy spectrum coming into the sort of first Floquet zone, and that gives us basically a lot of avoided crossings near zero energy or near zero quasi-energy. And so what actually is happening over here is that each of these avoided crossings can give you some evanescent transport, and it's the sum. And there are many, many, many of these because we're looking at this low frequency limit. And so it's basically summing over all the contributions from these different avoided crossings at higher and higher Ks that lead to this approximate power law. I can tell you more detail on that if you're interested. So that was the study that I did with Asa and my. How long do I actually have? Right. 10 minutes. 10 minutes. Okay. So in the last 10 minutes, what I want to tell you about are some things we've done since, and this is work that REG has done some heavy lifting on. So we wanted to go back to some more basic things and kind of an easier limit, which is the high frequency limit, and understand in more detail how the topological transitions work. Right. So this is graphene. This is a picture of the band structure with no light shining on the sample. When we turn on the light at high frequency, we get gaps opening up. So these are the K and K prime points. Later I'll call it the K plus and K minus. Maybe I should start calling them that now. The thing to think about, this is a very high frequency, but as we lower the frequency from large values, eventually you're going to have, let's say, this region over here coming to the surface, the edge of this Floquet zone, and you'll actually start to get at mixing states up here with the states in the band down there. And it's something about that that allows you to get these transitions. So between the different transitions between the different topological states. So this is a picture here of some representative points in the two bands as a function of decreasing frequency. And we've highlighted some of the high symmetry points, the gamma, M, and K points. And you can see that it's these high symmetry points that very often are actually able to get all the way to the zone boundary and touch the state on the other side. They actually are crossing. You're getting the degeneracy. For some reason, we're not getting level repulsion, and so that's the place that we're able to get a transition and a change in turn number in the band. And this happens for, basically it happens in different places for all high symmetry points with the K and M, the N point that happens typically at zero energy. It can happen at the gamma point, both, and also at the K points at either zero energy or at the Floquet zone. Okay, so it's those gap closings that allow us to have the topological transitions. And we want to see how this really works. So if we go back to the Hamiltonian, this Floquet Hamiltonian that we need to diagonalize, we can write it in this form in the type binding model. This Z, which is sort of the active part of the Hamiltonian, is something, it's really a very simple object. It's just this exponential of the momentum plus the vector potential, dotted into nearest neighbor vectors summed over those three nearest neighbor vectors. And so if you look at this object at a high symmetry point, for example, the simplest one is actually the gamma point, where you set K equals 0, what you recognize is that once you set K equals 0, in some sense you're not distinguishing among any of the points in the lattice. They're all basically going to have the same amplitude and the same phase in the sum that this represents. And so now when I turn on my vector potential and it's rotating around at some frequency, because we're not really distinguishing the different nearest neighbors, as the A sort of moves through these positions, for example, it starts over here. When it's over here, the Z has actually returned to exactly the same value as it was over here. And what that means is that the frequency associated with the Z when you're at the gamma point is actually the lowest Fourier component basically is average with respect to time. You can write down the eigenstates of this very, very easily. And they're characterized by an integer m, which is basically the different Fourier components of the light. Okay? But you have all these extra pieces from the Z, the parts that really are time-dependent. And because of this phenomenon that you've tripled the frequency, you can't actually admix just any two values of m through this A. It will only be m's that are actually differ by a number, basically differ by a number divisible by 3. And that's what allows topological transitions to occur. So for example, over here, where we have this gamma point, where they first meet up at the Floquet zone boundary, this m is a 0, this m is a 1, and they're going to be able to cross, because the difference between those two is not divisible by 3. They're not at mixed. And that's actually one point where you in fact get a topological transition. One thing we thought that you should be able to see when you go through these topological transitions, if you look at transport, is sort of an enhanced transport. It's a metallic conductivity of order e squared over h. And for some of these, it does work out nicely. For some transitions, you'll indeed get something of order e squared over h in transport. So like this transition over here does indeed do that, and this is a transition involving the k point. But sometimes we saw, to our puzzlement, that you don't really get much conductivity at all. It can actually be very, very low, even though there's no gap in the spectrum. That's an example of this. An example of this is over here. And eventually we realized that the reason for this is that the states that you actually admix, that you're allowed to admix at the high symmetry points, if they don't include the m equals 0 state among them, they're actually going to have very little overlap with the states of the Fermi energy in your leads. So it's very hard to access the states, even though they're there at the energies where you're trying to push electrons through. So to test this idea, one of the things we recognize is that, well, maybe we can do something that would cause this m equals 0 state to be admixed in. The reason it's not there is because this conspiracy between the temporal and spatial symmetries of the system. So if we spoil one of these, like spoil the spatial symmetry, maybe we can start to see something about this. So obviously disorder is something that will spoil the spatial symmetry. So you can throw some impurities in, and if you just throw some impurities randomly into the sample, basically you'll get this blue line over here. So initially, at small lengths, there is quite a bit of enhancement of the conductance, but eventually localization physics kicks in and makes it very hard for the system to conduct if you get too long. On the other hand, you can do sort of a partial disorder where you just put the disorder near a lead so that we don't involve localization physics, and that's this red line over here. So you see that we get something like 2 orders of magnitude enhancement by putting disorder, by putting dirt in the system. So that was sort of a little surprise for us. Okay. So last 5 minutes? Or not quite, or less 1 minute, okay. Oh, all right. The last trick, I'm not going to tell the whole story. The last trick here that we thought about is using this physics to do some kind of valleytronics. In particular, we had the idea that you could actually make some kind of valley valve out of this. So here we were looking at the transitions near the K and K prime points. So there's something like what I showed you for the gamma point in terms of the symmetries here. There's not quite, but it's similar to a tripling of the frequency, which is good enough. And there's also an inversion symmetry that is both spatial and temporal. And this part over here actually guarantees that if you get parameters that close the gap for one valley, you're going to get it for the other valley as well. And so the question was, can we get to a situation where we make these two not equal to each other, but maintain this relation over here so that you can close the gaps if you like, but not necessarily at the same set of parameters for both valleys. Right? And we've discovered that you could do this if you add in a harmonic, a fourth harmonic of the original light, and if you have a phase offset, as long as it's not 0 pi basically, then you would get get this relation that we have. We get this pair of relations that we have. And so what that allows you to do is open a gap basically at one valley while keeping the gap closed at the other. And that means now we've got a system where we can push current through from one valley but block it for the other. Right? So this is kind of valley-valve action. So this is just showing that you can figure out various parameters for which this will work, where you get basically closing the gap from one valley but not from the other. And so I actually spent a lot of time figuring out what kinds of geometries might actually be useful and possible for doing this. So this is sort of a picture where we have the sort of main color of light shining on the sample, and then you can shine on two halves of it. You can shine the 4 omega component with basically two different phases, and by choosing the relative phases of these two components, you can allow a valley current for just one of the values of the whole system, where you can change the phi of r relative to phi of L so that you shut off both valleys and that no current would be able to get through. Okay, so looking at one of his geometries, this is basically showing a polarization, a valley polarization you can get. And one of the nice things about this is because it's a bulk effect, the polarization actually improves as you make the system bigger and bigger. As opposed to sort of the earlier ideas that people have, which, for example, use edge states to use edge states to implement valley electronics in graphene. There you have a problem really mesoscopically designing your edges. And the size, well, the bigger the system, the more trouble you'll have having well-defined edges over a larger system. But in this case, the system actually basically improves because it's a bulk effect. The larger the system, the more firmly it's going to be able to block the current from just one valley. All right. So I have some more details, but maybe I'll just stop since I'm out of time. So let me just say one thing. Thank you for listening. And for Asta, Leben sollst is 120 Jahre, something my parents would have said. If you're not familiar with the Yiddish, it basically means may you live to 120, and that the next 60 years be as inspiring, as interesting as the last 60 years. I guess the experimenters have to learn how to work with different materials, and he knew how to work with that different material. He was able to get that out, sort of design it in a time frame. So we'll see. Yeah.
So the question that you raised is still an open question, right? What the question numbers we use.
Yeah, I don't know if there's a universal
But there's some limits that you you know the answer, like high frequency?
I think at the high frequency, well, I'm not sure I know. I'm not sure I know the answer to any of these limits. There are some studies, so Nitanel has actually done a very nice study of this, and you get some numerical